Cavitation and NPSH. Cavitation and its relationship to net positive suction head continues to be one of the more intriguing subjects in any discussion of centrifugal pumping hydraulics. Cavitation is generally accepted as a two-part process caused by the changes in pressure as the liquid moves through the impeller. The first part of the cavitation process occurs when the pressure falls below the vapor pressure of the liquid and vapor bubbles are created in the eye of the impeller. The second part of the process occurs in the areas of higher pressure on the vanes of the impeller. As the impeller rotates, the centrifugal action moves the bubbles along the vanes to the high-pressure areas, where they are collapsed in a series of implosions. These implosions develop energy levels well beyond the yield strength of most pump materials and create small cavities in the metal. This condition is accompanied by noise, high vibration levels, and a reduction in the total head developed by the pump. As the severity of the cavitation increases, all the effects will increase. Damage to the impeller also increases, and under severe conditions, damage will also extend to the casing. Similar characteristics can also be created by other operating factors, which are sometimes confused with cavitation. Suction recirculation takes place between the vanes and causes pitting damage along the trailing or concave side of the vanes. This condition is generally accepted as being caused by operating the pump at very low flow rates. Discharge recirculation occurs at the outer diameter of the impeller and results in pitting damage at the tip of the vanes and sometimes near the cutwater of the casing. This can also be caused by a low flow condition or by a hydraulic design problem referred to as vane passing frequency. Air entrainment defines a wide variety of conditions where the vapor bubbles are already in the liquid before it reaches the pump. Unfortunately, it causes the same pitting damage and in the same location as cavitation. This makes it very difficult to identify the real cause of the damage, particularly as they can happen at the same time. In air entrainment, the vapor bubbles may be an inherent part of the liquid, such as in any effervescent or fermenting process, or from an operating temperature close to boiling point. Air could also be drawn into the system as a result of poor suction tank design, or even created in the system by inadequate piping. All these factors result in pitting damage caused by the formation and the subsequent collapse of vapor bubbles. The differences lie in the way the bubbles are formed and the location of their resultant implosion. The most common cause of pitting damage is true cavitation, which takes place when the vapor bubbles are created by insufficient pressure energy at the eye of the impeller. The pressure energy required to avoid the formation of vapor bubbles under this condition is referred to as net positive suction head, or NPSH. The design criteria of every impeller requires the supply of a minimum level of NPSH for its optimum performance. This minimum level of pressure energy is identified as the NPSH required and is strictly a function of the pump design and its rotational speed. The pressure energy required by a pump is made available from the system in which the pump operates. It is identified as the NPSH available and is solely a function of the system design. Consequently, to avoid serious cavitation damage, the NPSH available must be greater than the NPSH required. However, if the NPSH available is less than the NPSH required, true cavitation occurs, and there are only two basic approaches which will eliminate the problem. Either we decrease the NPSH required, or we increase the NPSH available. First, we'll consider the possibility of decreasing the NPSH required by the pump. This can only be achieved in these limited number of ways without changing the pumping conditions. 1. Increase the eye area of the impeller. Unfortunately, this could cause recirculation difficulties and should only be considered as a last resort with the involvement of the pump manufacturer. 2. Install a suction inducer at the eye of the impeller. As very few pump manufacturers have suction inducers available, their practical application is severely limited. 3. Use a pump with a double suction impeller. 4. Use a slower speed pump with a larger diameter impeller. 5. Use a number of lower capacity pumps in parallel. 6. Install a booster pump in series at the suction of the main pump. While the first two options refer to modifications to the existing pump, all the other options require the purchase of at least one new pump. It would therefore appear logical to explore the other approach, that is, to increase the NPSH available from the system. The NPSH available from a system is made up of only 4 factors: the static head over the impeller centerline, the atmospheric pressure on the surface of the liquid in the open suction tank, the vapor pressure of the liquid, and the friction losses in the suction line. The NPSH available must be calculated in absolute values from this equation. A detailed study of the 4 factors should reveal all the possible ways to increase the NPSH available. In reviewing the static head HS on the basic system, it is obvious that this can be increased only by raising the tank, by raising the level in the tank, or by lowering the pump. This would also be the case even if the pump was above the level of the suction source, and the value of HS was negative. To increase the value of the pressure HA in the suction tank, the only option available is to pressurize the tank. To effectively reduce the value of the vapor pressure HVP, we must cool the liquid. To reduce the friction losses HF in the system, we can improve the suction piping by increasing the pipe diameter, by reducing the pipe length, by changing the pipe fittings, by modifying the valve type, or by reducing their number. These are the only options available which can alleviate the problem without changing the pumping conditions. In the vast majority of cases, one or more of them will provide enough additional NPSH available to satisfy the needs of the pump. By taking these same factors into account during the design and construction of any new system, the problem can be prevented from occurring in the first place. In designing a new system, it should be noted that the acceptance measurement of the NPSH required by the pump is standardized at a level where mild cavitation is already taking place. However, only a 3% reduction in total head will be evident. At this point, the implosions are rarely severe enough to cause any significant pitting damage or vibration. Even when it is impossible to take any corrective action, a final option is to live with the cavitation and try to minimize the damage to the impeller and the effects of the vibration. The impeller damage can be reduced in a number of ways, depending on the impeller material and the service in which the pump is operating. A simple change to a stronger impeller material will raise the yield strength and minimize the damage. In some cases, a hard coating on the existing impeller is an acceptable solution. Vibration will cause premature failure of the seal and bearings, but this can be minimized by reducing the shaft slenderness ratio. In addition, short overhang pumps with large shaft diameters have been specifically designed for applications where vibration develops from unstable hydraulic conditions. A clear understanding of both cavitation and net positive suction head and their relationship to each other will provide practical solutions to the problems of cavitating pumps.